Good morning, everybody. Welcome to today's meeting. Today we're going to have a meeting about a Modbus demonstration. So we're going to apply some of what we covered in last week's meeting. So we're going to use the NXF4000. And first thing I'd like to say is if everybody could please mute their microphones. That would be great. So today, in addition to myself, I'm Carlos Escorski. I'm a product manager at FireEye. We also have Richard Long, he's another product manager, and he's going to be on the line monitoring the chat. So if anybody has any questions, please type them in the chat, and as appropriate, Richard will chime in and bring them up. So today what we're going to do is we're going to just do a practical test of Modbus, show you how you can use tools that you should have on your computer or can easily get for your computer to test a Modbus connection. So the first thing I want to do is start at the FireEye website. So I'm going to click on a link that I have prepared. And we're going to bring up the bulletin or the manual for the NXF4000. So when the website opens, it's going to open to FireEye.com to the main home page. I'm going to click on Products, Burner Controls. And then when this page opens, I'm going to look for Efficiency Control for NXF4000 parallel positioning. I'm going to click on that. Down here under manuals is where I'm going to have all of the bulletins. So the one I want to open is the main bulletin NXF4001. So on that. And what I'm looking for is the connections for Modbus so I can show you where we will make our connection. So I'm going to go to page 23, and this may take a second to navigate to. So Modbus is a two-wire connection. So this is Modbus RTU. It's a serial connection using RS485. And it is two wires in a twisted pair. So the reason the pair is twisted is to reject any noise. If noise interference hits one wire, it'll hit the other wire equally. And when you measure the voltage differential, if there's 1 volt of interference on each wire, you're still going to have a 5-volt differential between the two. So it's really good at rejecting any sort of noise. So the connections we want to make, since it's two wires, on P12 here on the side of the NXF4000 is a terminal block. And right here it shows a cursory description of what each terminal does. And you'll notice there's terminal 1 and 2 are M-Bus A and M-Bus B. And those are the terminals that we will be connecting to. We also have several other Modbus connections as well. Sequencing A and B, servo A and B, as well as O2 A and B. So there are 4 different Modbus connections on the control. If I go down to page 25, where it has a little bit more thorough description of P1, P12.1, and P12.2, we'll see Modbus RTU A and B is for touchscreen and BAS access, and BAS means building automation system. So that would be your building automation or your PLC. So I'm going to show you a video real quick that I made since I don't have all the cameras to set up to do this live. Just to show you, and before I start it, let me go describe a little bit what I'm going to show you. So in order to make this connection, we're going to need a serial port. So let me pause this. So before we can make a connection to the NXF4000, we're going to need a serial port on our computer. So formerly, laptops, old computers, had an RS-232 serial port almost all of the time. Nowadays, computers don't have serial ports built in, so what we have to do is we have to use a USB to serial port converter. So since we're using RS485, what we need is a USB to RS485 serial port converter. So this first one I'm showing you, so this is just the generic converter that plugs directly into the USB port. You can get ports like this of all different shapes and sizes and brands on Amazon very easily and inexpensively. So this kind of serial port is one that you could use. It has the terminal markings. You can't really read them on the back. Pretty straightforward. It has an A and a B terminal, so it has the 2 terminals we need. Here's another variety. And this one is from Automation Direct. And this one, instead of using terminal blocks, uses an RJ45 connector. So you would need to know the pin out. Just another variety of a USB to 45 converter. And so lastly, the one that we're going to be using is this one. And this one we offer through FireEye. It's called the UC485, and you can get it through the distributor or directly from us. And this is the one we're going to use today. So it has, this one actually has 4 terminals on it, so it can be used with 4-wire RS485. we're going to be making the connection to TDA minus and TDB plus, and it has a mode, it has some jumpers on the back, let me show you, that you can set for 2-wire or 4-wire mode. So this set to 2-wire modes, we'll only be using those two terminals. And when I make the connection, I'll show you where I'm making it. And there's our part number UC485. So I'm going to use a twisted pair of the red and the black wire. I'm going to put the black wire on TDA minus because it's the minus terminal, which is going to connect to Modbus B on the NXF4000. And if I made a mistake, the nice thing about Modbus is that I can simply swap the wires around without any damage to the equipment. It's not going to hurt anything. It just won't work when it's connected backwards. And it's also hot swappable, so I can change it without having to turn everything off. So after I make the connection, I'm going to plug it in to the USB, and that's all I have to do to make that connection. Okay, so now once we have that connection, let's connect it on the other end. So we have the NXF4000 side. And this is on one of the trainers that needs to be cleaned up a little, so I apologize. Start this for the condition of the wires. But this is that P12.1 and P12.2 that we just looked at in the bulletin. So I'm going to connect the red wire to A and the black wire to B. And that's the only connection I need to make on the NXF4000 side. So we're going to have to do a little bit of configuration, but we'll get to that shortly. Okay, so now that I've made the connections, I actually have to figure out what my COM port number is for the serial port. So the serial port, it's not enough just to connect it. You need to know the COM designation for the program you're going to use to do your test. So it's going to have a designation such as COM1, COM2, COM3. So the way I do that is I use Device Manager. I just click on the Start menu, and I just start typing Device Manager. So I'll type DEV, and it'll pop up right here. That's how I open it. There are other ways you can open Device Manager. And when you open it, it's going to bring up a list of your devices. So what we want to do is find ports, COM, and LPT. So when I expand that, it's going to show me which ports I have connected. So you're always going to have a couple on your laptop, like these Bluetooth ones are always connected, whether anything's plugged in or not. So I actually have 3 serial ports plugged in right now. So I know the one that I want to use is COM1, but normally you're going to just have one. So you're going to plug it in, it's going to pop up as COM1, and if you wanted to verify, you can unplug it and check that it goes away and comes back, etc. I'm using the other ones for some other things. So COM1 is the designation that I need to set into my program. So now that we've looked in Device Manager, we know that we're set up for COM1 and that our serial port is actually connected. Because this would also be where you would see if you plugged in the serial port and it didn't have a driver installed or something that the serial port wasn't working, it would show you with a triangle, a warning triangle, that the device was not recognized. And then you would know it isn't going to work for that reason. So now that we know it's got a COM port and it should work, let's move on. So now I'm going to go back to the NXF4000 itself. This is the NXD410 touchscreen. This is our replacement for the keypad on the NXF4000. And so I'm going to, from the home screen, and you'll notice it looks similar if you haven't seen this yet, has the same screen that you have on the NXD410. I'm going to go up to Communication Setup. And this is where I'm going to set up the baud rate and the unit address. So I'm going to set up, and I'll explain this in a minute in the Modbus bulletin, but I'm going to set up the baud rate. I'm going to change it to 19,200 and apply that. And then I'm going to change the unit address to 1. And they scroll around so I don't have to go down. Okay, now I'm going to go back to the home screen. So now I'm going to go back to the FireEye website, which is still open. And I'm going to open a different bulletin. I'm going to open the Modbus Communication Bulletin MOD 4001. And right on page 1 here, it's going to start with a little description of how Modbus works, a little bit of technical details that you don't need to know about. But towards the bottom, it's going to tell you the communication parameters that you need to know. So it tells you here that some of the settings are fixed. You can change the baud rate, which we just did. You can change the unit address. But the data bits, the parity, and the stop bit are set to 8 data bits, no parity, and 1 stop bit, and those are fixed. You can't change any of those. And it tells you that here on page 1. So the first thing we're going to do is, or next thing we're going to do is go down to the mapping. and we're going to find something that we can read so we can get started on actually testing it. So I want to find something that I can change very easily. So I've chosen the servo position, because if we go back to here and we scroll down, we can see the servo position right now is 1.0 degrees. So if I go back to the Modbus listing and I want to find servo position, it's 40080. And before I get down to that, let me explain what that means. So if you remember from last week, we have different types of registers. And if you didn't see last week's, it's available on the YouTube channel to watch, and it's called Introduction to Modbus. The holding register is going to be in 4x format, so it's going to be 400, in our case 80. Where it says message address, it's going to have another address, and that's going to be one fewer because that's the address if you were to start from 0. So in our case, 40080 is going to, if we started at 0, it would be 79. So if we start with 400 style addressing, it's going to start at 40001. So it is going to comprise of one register, and it's servo 1 current position in 0.1 degree increments. So since we're reading 0.1 degrees, the servo position in Modbus should read 10. So let's try it. Okay, so what I'm going to do before we get too far with that is I'm going to show you the tool I'm going to use anyway. I'm going to use a tool called Shortbus Modbus Scanner. So I have a link to that because this is a free tool that you can download, and it has a website. It's sites.google.com/site/shortbusdll. When you get here, you can download Shortbus Modbus Scanner. There's a link provided. So let me open that. And what I need to do now that this is open, the first thing I need to do is specify my connection, which is COM1. And we know the COM port number because we checked that with Device Manager. Then I put in the baud rate, which is 19200, and I put in the node address of the device I want to talk to. Now keep in mind, you can talk to multiple devices. So we could have connected a second NXF4000 or a third, or we could have even connected an E110 or a micro M or any other device connected together by connecting the daisy chain one device to the next with the A and the B wires. And also the baud rate, as long as the baud rates match, you can connect multiple devices. Now some devices such as the E110 and the micro M have a 4800 baud maximum, and the only way we could connect them together with an NXF4000 is if we actually set the baud rate of the NXF4000 also to 4800. But since this is the only device, we've picked 19200. That's the baud rate we'll use here. So we set the node address to 1. The starting address is what we want to read, and we want to read 40080. So I don't type 40080 here, I just type 80. Because the type I'm reading is set by this read function, read4x, so that part 400 is implied. And then the length I want to read is 1. So now when I hit connect, let's see what happens. See, I have good polls. It's got total polls and valid polls are matching. I got data here, 10, which matches what we're expecting to read. It's actually oscillating between 9 and 10, showing you that Modbus is actually more accurate than the touchscreen itself because it sees the slight change. Now let me show you another video real quick as another indication that you're working. It's called activity. So we're seeing the polls increasing, but on the device itself, you see these activity lights blinking, and that's your positive indication that your Modbus is working. So that is the actual physical connection verification. So that's great. So we got communication, and I'm going to actually hit the start button so we can let this purge, and we can watch this change in real time. This should go to 90 degrees for purge, and you can see the Modbus value is going to go all the way up to 900. All right, so I'm going to let this start, and we're going to read something else in the meantime. So I'm going to go up to the Information tab, and I'm going to see how many system hours we have, system on hours for this unit. So we can read that with Modbus. All right, so here we have system hours 204. I'm going to go back to the Modbus bulletin so that we can find that information. And I know it's 40003. So I'm going to go up. System on hours. And you'll notice that it's a little bit different. the address 4003, but the words requested are 2, and it actually encompasses 40003 and 4, both. And then in the description, upper 16 bits and lower 16 bits. So this is information that can potentially be too big for a 16-bit integer, and the limit for an unsigned 16-bit integer is 65535. If you had more hours than that on your unit, you're going to need a second register to handle the overflow. So 2 registers are reserved for that. So what we're going to do first is we're just going to read the first one and see what we get. So I'm going to disconnect, and I'm going to change the address we want to read to 3 and hit connect. And so we read 204 hours, which matches what this says here. Now, in Modbus, all of the data is in registers as 16-bit information. It's all very generic, and how you interpret it really determines what it means. Case in point of the servo, 900 by itself doesn't mean anything. You have to know that you put a decimal point in there. Or if you were to read 2 registers here, which you're supposed to do to read this, I'll change the length to 2. You'll see the first one is 204, the second one is 0. Together, that doesn't really mean anything to you. But if you interpret it, and in this program I can change the result format, so if I interpret it as a 32-bit number, I'm still going to read 204, but now it's actually properly combining the 2 registers. So if my number was bigger than 65535, I would see that. And I will demonstrate that using our shortbus server momentarily as well, so you can really see how that works and maybe understand it a little bit better. All right, so now let me find another register that has another different format. So I'm going to go to 40030, and this is combustion efficiency. So combustion efficiency, you can see in the value, has a range from -1 to 999. And this is also going to have 0.1 degree accuracy, because 999 would mean 99.9%. And -1 will signal that the efficiency is unknown. So let me bring that up and see what we see. So I'm going to change this back to unsigned integer 16-bit like we had before. Change the address here to 30, length of 1, and hit connect. So I'm reading 65535. And if we look back at the bulletin, that is not a valid number. That is not a valid value according to this. But that's because I'm not interpreting the data correctly. The register's contents are proper, but I'm reading it as an unsigned integer. What I need to do is look at it as a signed integer. And what signed means is it can be negative or positive. Unsigned means it can only be positive. So now if I make that connection, that same value is properly read as -1. And again, I'll also show that with my Modbus server so you can see a little better how that works. So let me do that now, actually. So let me close this. And I have a second serial port connected to the NXF4000 as well. So I can actually connect this at the same time and read data from here. So shortbus server is going to allow me to actually create Modbus values that I can read myself. So I'm simulating a device, basically. So in this case, I'm going to pick the same baud rate, because they all have to have the same baud rate. I'm going to give it the node address of 11, and I want to display 10 registers. So I connect my server, I connect a slave with node 11, and it's populated with the values 1 through 10. So let me open Shortbus Scanner and move it down so we can see both. Connect it to COM3 this time, so a different COM port. And if I was to read from 1 like I was before, that's still going to be my NXF4000 because that's still connected as well. But I don't want to read from the NXF4000. Now I want to read from 11 because that is my server over here. And if I do that, I will read the same values 1 through 10 that I had on my server, because this is now the Modbus Slave that I'm reading from. And the reason I'm doing this is so that I can change the data formats and we can see it on the other end. So here I just have a bunch of raw data. If I was to read, let's say I wanted to read the first register, or actually it's the third because it's the same address. I wanted to read the system on hours again. So I'm going to read 2. And if I change this to read 204 like we were reading on the NXF4000, and a 0 here, I can write those. I'll read the same 204 that I was reading on the NXF4000. If I read that as a 32-bit, I'll also see 204 like I was seeing before. And as the hours increase, it gets to 60,000 hours. It's no problem. I see 60,000. And I get to 65535. I'll read everything okay up to here. Now, on this end, the format isn't changing. The numbers are just raw 16-bit data. But if I wanted to read 65536 on the hours, what's actually going to happen is this is going to change to a 0, and this is going to change to a 1. And now I'll read 65536 on my scanner. So that's how the two registers work together, because it takes all 32 bits and recreates a bigger word out of them. So now if I wanted to get to 65537, this would change to a 1. Now as this increments, my number will go up. So if this was back at 204, it would actually be 204 plus 65535, because that second bit is incrementing it to a larger number. So that's how two work together. And now I'll show you with an unsigned, or with a signed integer, sorry, how we can get a negative number. So if I read this data as a signed integer, so 4003, it's going to read 204. And if I change this value to, say, if I write it from this end, and I want to make this say -1, and I send the write, it's going to read -1 over here, because this is formatted to be a signed integer, so it's formatted signed here. It's going to write the value here, but since this is displaying as unsigned, the number is going to show up differently. It's going to display as an unsigned, but the value is the same because the bits are the same. So if I change this to display as signed, it's going to show up as a negative number here as well. So that's just how I wanted to reiterate that the data itself in the 16-bit registers is just generic 16-bit data. How you interpret it is what is important. So let me close these and we can move on, because we have a couple different types of registers to look at. So next we have a string, and actually this is going to be on 40347, so I have to scroll down a few pages. And 40347, which is going to occupy 10 registers, it says PCV set point string 22 character string. So let's put in that address and see what we get. So I'm going to have to open Shortbus Scanner again, and I'm going to use COM1 again, and I'm going to read 347 like we want to, length of 10, and set the baud rate correctly, and hit connect. So this is the data I get when trying to read PCV set point string. It's just a bunch of 16-bit numbers. I don't understand what they mean. But that's because I'm not reading them in the correct format. So I'm going to disconnect and set this up to read as hex or ASCII. And ASCII is the coding to turn a hex code into a symbol, a letter, or a number, or something for, usually it's used for keyboards as well. For Modbus, for anything that's going to convert a number into a letter or character, you're going to use ASCII. So because ASCII is going to use an 8-bit character, each 16-bit register contains 2 ASCII codes together. So when I connect this to display as ASCII, I'm going to see the number in hexadecimal. That's why some of these have letters. And it's also going to show, because the Shortbus Scanner is going to show it as the ASCII codes themselves. So I'm going to open one other website, ASCII table. I'll just show you how you could manually translate this. So let's look at the codes first. So the very first one, we have 45 and 53. So that number is 4553. So on the ASCII table website, 45 in hex, and we want to use the hex column, not the decimal column. 45 in hex is going to be an E, and 53 in hex is going to be an S. And that is exactly what we see, except that we're swapping them around. Because you can also, because you have 2 bytes, the order of the bytes is important. So we're reading them in what's called normal order, which is going to reverse them. And then there's also swapped order, and if I hit connect, it's just going to show the same data, but backwards. It's going to swap the 2 bytes around and make the letters in the other way around. So if you're going to read ASCII data and it seems to be backwards, then you would just swap around. So I also have the ability with Shortbus Scanner to actually create a full string out of this. And it's going to keep reading the string until it gets to the null. And null is just 0, 0. And null means that the string has ended. So a space is hex 20, which is different. Null just means that the string is over. So it knows to stop creating the string. because it's going across multiple registers, it'll keep writing the same string until it hits a null character. So when I choose to display this as a string, it's going to show me the whole string. And you can see here, set point 1 with a bunch of spaces and then 100 psi is our string directly from the screen. Set point 1, 100 psi. If I was to change the set point, this string would change. So let me go back here. Also, if I showed this as swapped, you can see that it would clearly be the wrong message, and it would be pretty easy to figure out that it should say set point, but it doesn't because the byte order is swapped. So that's how a string would work. So next we got another type, and this is the last type before we get to some writes. And this is bits. So let's go to this, back to the bulletin. And this is 40018. And what this is all the digital inputs plus the call for heat or limits complete input in a single word. So since a word is 16 bits, we can have 16 bits of data that are 0 or 1 and embed them into one word. So that's exactly what this is doing. This is taking the one word and putting the status of digital inputs 1 through 15 as bits, as well as the call for heat in the 16th position. So that's 40018, and that is a length of 1. So let's look at that. So I'm going to put in 18, and then I'm going to look at that as an unsigned integer again, and just a length of 1. And what we're going to see is 33346. So that doesn't make a whole lot of sense. But let me show you in Notepad, and this will take a second, but I think it'll help you to understand how this works. So, make this a little smaller. So if digital input 1 is on, the value on this register is going to add 1. If digital input 2 is on, it's going to add 2. Now digital input 3 is not going to add 3, it's going to add 4, because what this is powers of 2. So this is going to be 8. Next one is going to be 16. And I'm just going to type all of these real quick. It won't take that long. And digital input 7 be 64. Digital input 8 be 128. Digital input 9 be 256. Digital input 10 would be 512. Digital input 11, 1024. Eventually you would maybe memorize these like I did. And your software, your PLC, etc., can usually abstract this so that you can not have to actually calculate it yourself, but it can tell you which bits are on directly. Almost at the end. And this one would be the limits complete. And most devices are going to have something similar to this. It's going to tell you which bits correspond to which inputs. So what this means is 33346. Some combination of these is going to equal 33346. I don't know exactly what combination that is, but if we were to add up the combination of which inputs are on, that's exactly what it would equal. Now we can also look at this as binary and not have to do that calculation. So here we can connect this as a binary, and this is going to be the 15th. So it starts at 0, so this is going to be the 15th bit, which tells us call for heat is on, DI 15, 14, etc., down to DI 1. So if that DI is on, this will be a 1, and if it's not, it'll be a 0. So that's how you read bit data embedded into a word. So lastly, let me show you guys how we can do a write, because that's the fun part, I think. So let me disconnect this, turn this back here. So I'll go back to the bulletin. The information that we can write to the device via Modbus is at the end of the bulletin at 41001. It begins at that register. So this section of writable data, this is the data we can write. So the first one is reset. So I'm not going to do a reset, but I'll have one disclaimer on reset. If you're going to write any sort of flame safeguard reset over Modbus, the device you're applying it from should be within sight or sound of the burner. You shouldn't do this remotely, because that could be potentially unsafe. So the first one we're going to look at is burner control on off, and the address for this is 41002. Okay, so I'm going to look at 1002, length of 1, and I'm going to hit connect. Okay, so it shows it as a 1 right now. So this is physically linked through Modbus to this button. So if I turn this off, this will turn to a 0. If I turn it on, it'll turn to a 1. I have to wait a second for it to post-purge before it allows me to. This will turn to a 1, and it'll turn back to a 0. So, but I also can write this over Modbus. So with my tool here, Modbus Scanner, I can double-click this and get up a write window. And if I was to try to write a 1 now, it's going to fail, and then I'll explain to you real quick why. So I get no response or connection error. So by default, Shortbus Modbus Scanner is going to try to make the write as using function code 16. And function code 16 in Modbus is write multiple registers, and you specify the length. So by default, this program is going to try to use function code 16 and write a length of 1, which is the same as the function code 6, which means write single register. It's functionally the same. But the NXF4000 wants the write to be using function code 6. So I do have an option to use function code 5 or 6, and 5 is for writing bits, 6 is for writing words. So if I send that same write using function code 6, it's going to work. You can see this turns to a 1, this turns on. So I'm actually going to let it start. But that's how I can write to that button. Next, we're going to write to the manual auto button, and we're actually going to write a firing rate. So let me go back to the bulletin so we can see the addresses for those. And those are right below. So 41005 is burner control auto manual, so we'll set that 0 or 1. And that's going to also set the manual auto button on the screen itself. And then the manual firing rate we can also write from 41018. And these are both just unsigned 16-bit integers. So I'm going to remember both of those. And I'm going to this is going to be starting in the meantime. I'm going to bring up all of these at once. So I'm going to look at 41005, and then I'm just going to specify a length of 20, so it'll cover both of them in the same read window. Because you can actually have a length of up to 125 that you read. And depending on the device, some devices may not support that much in one read operation. You'll have to read the specifications. But I can read that, and I see that right now 41005 is set to 0. It's not in manual. But I do have to wait for it to actually go to auto before we can set that. Which does bring up something I did forget to mention, and let's look at that real quick before we do this right, because it's a good time for it. I did not show you how an enumerated list works, which is the status. So that's actually the very first register, and that's operational state. So let me look at that while this starts, and then we'll go back to this, right? Right now our operational state is 13, and that's going to match MTFI right here, state 13, now state 16. And let me just show you where that is in the NXF4000 bulletin. It's on page 96. I just kind of forgot about that one, but this is something else that's pretty common with Modbus. It's going to be a value that by itself doesn't mean anything. It's just going to be a number, but you have to interpret it as the operational state by looking at a list. So the operational state is 16 means auto, 1 would be standby, for example. And on page 96 of this manual, it'll show you the full list. One of them is going to stand for lockout, purge, etc. So all of the operational states you can read from that one number by itself. So let me go down 96. And this shows you all the operating states as numbers. So this is really helpful if you wanted to map out the progression of the control starting. You can read the state with Modbus and show that it's in move to ignition, purge, PTFI, etc. You can show that by just reading that one number. So I'm going to go back to where I was. So 1005, length of 20. And now that we're in auto, we can actually send this, put it in manual. So the first thing I want to do is to put it in manual. So that was 41005. So I'm going to double click that. Going to use function code 6, and I'm going to set this to a 1. Now when I hit write, the hand should light up because that's the same as putting it in hand or manual on this display. So we have a manual mod rate of 40% right now. And if we look at the register in Modbus for that, we see 40% as well. But this is a writable point, so let me open that. And right here, I could write anything I want. But it has to be in the valid range of 0 to 100. So if I tried to write 500, we can't modulate to 500%. So let me click use function code 56. And it's going to take an exception to that and give me an exception error, which we covered last week what that means. But it's basically telling me you can't write 500 to this. That's too much. So if I wanted 500, if I wanted 50%, I'd write 50 instead. It'll take that. It'll go to 50%. Now, Modbus Shortbus Scanner has a cool feature where we can actually automate the write. So I'll do write automatic within a range. And I'm going to start at 0, and I'm going to have it go up by 5 at a time. Or sorry, I'm going to have it go up to a maximum of 100 by 5. And I'm going to have it write every 300 or every 3,000 milliseconds, which is 3 seconds, automatically send this write. So it's going to write the firing rate automatically. Every 3 seconds, it's going to increment it by 5. So it goes 5, 10. You can see it changing here. Because in your regular PLC program or building automation system, it's going to be continuously changing the firing rate as it needs to. So you can write it as much as you want. That's my point. So to control your process. So now that we've done that, I'm going to put this back into automatic. So I'm going to close the window to write this. I'm going to write a 0 to go back to automatic. And that's basically everything. So Richard, were there any questions that anybody had?
No, there weren't, Carlo.
Okay. So that's everything we have for today, and I want to thank you guys for watching. And to kind of recap, Modbus is a very simple protocol, but very powerful. All of the data is presented just as unsigned 16-bit integers. How you choose to interpret it is very important. You can read, you can have letters, you can have floating point numbers, you can have larger numbers, you can have all that stuff. It just takes work on your end to repackage the data. There are other protocols that are a little bit more robust and give you a lot more information, such as BACnet. There's also industrial protocols like Ethernet IP. We're going to soon come out with a communication gateway that's going to allow you to take our Modbus interfaces that are available on almost all of our products and convert that to those protocols, Ethernet IP, BACnet, MSTP, BACnet IP, Modbus TCP. So you'll be able to actually convert those protocols and connect multiple devices to one communication gateway. So that'll be coming out soon. So again, thanks everybody, and hope to see you for our next one, and have a good rest of your day.